Hi guys, this is titrations within acid base 107. This is part 2, and what we're talking about here is a titration between a strong acid and a strong base. This is an example of the same titration that we did in class. A little bit different concentrations, and also different is when we're asked to look at the pH, or how we're asked to look at the pH. So the example question says this: a 0.0200 molar solution of HCl has a volume of 100 milliliters. It is titrated with a 0.0400 molar sodium hydroxide, and you're asked to calculate the pH of the solution titrated after the following amounts of sodium hydroxide have been added. So just as a quick picture here, if we have our burette and our flask, in here is the HCl, and in here is the NaOH. And what we're trying to do is figure out what's the pH of this solution as this is added. So in our first one, we have 0 milliliters of sodium hydroxide added, which means that the concentration of the HCl is equal to 0.0200 molar. And since this is a strong acid, we're just going to negative log that concentration. And we get 1.7 for our initial pH. Okay, so pretty acidic. Next, we have, after 20 milliliters of the sodium hydroxide has been added. So the first thing you want to do, if it's not an initial question, is you want to write the neutralization reaction that's happening. And for any strong acid, strong base titration, the neutralization is going to be the hydrogen. I'm actually going to use H3O plus. So this is the HCl plus the hydroxide, and that's from the NaOH, makes H2O plus H2O. So this is the neutralization reaction. So once you have your neutralization reaction, and you don't have to write in the acid and the base here, it's just I'm using that for teaching purposes. Down the left-hand side, you're gonna write BCA instead of ICE. B stands for before, C again stands for change, and A stands for after. So with these guys, you're finding moles because you're actually doing stoichiometry. And what you're going to do is see how many moles of acid there are and how many moles of base, and then you subtract the smaller one of the two. So remember, to find moles, you're going to do the molarity times the liters to get to moles. Okay, so we have 0.02 molar HCl and 100 milliliters, so 0.02 times 0.1. And so for the acid, comes out to be 0.002 moles. And the sodium hydroxide is 0.04, and we've added 20 milliliters. So for the hydroxide, we're doing 0.0400 times 0.020. So 0.04 times 0.02, and we get 0.0008 moles. And the water, we don't care about this. And so if we look at this, we can see that only a little bit of sodium hydroxide has been added compared to the acid that's there. So we're going to go ahead and subtract the smaller of the two. And that's going to give us 0 moles of sodium hydroxide left over. And let's see what we get when we subtract this. And here, after, we get 0.0012. And this is moles of the H3O plus left. Now, in order for us to find the pH, we have to take this and turn it into a concentration. Okay, so if this is moles, we're going to go 0.0012 moles. And then we have to divide by the liters. Now that's the total liters, which means we're going to take our 100 milliliters that we started with, and we're going to add the 20 milliliters that we just added. So this is going to be over 0.120. So this is 100 mils plus 20 mils. So divide by 0.120. And our concentration of the H3O plus is equal to 0.01. And then if we negative log that guy, we get our pH equals 2. Okay, so we want to look and see, does that make sense with what we just did? We had a 1.7 pH to start with, and we added a little bit of sodium hydroxide, and the pH went up to 2, which makes sense. Okay, cool. All right, at the next one, we are going to have the same exact neutralization reaction. And we're still going to do BCA. This initial amount of H3O plus is still going to be 0.002. For the OH, is going to be different. So for the moles of OH, we're going to take the concentration of the NaOH, 0.0400, and we're going to multiply times the number of liters that have been added, which would be 0.050. And this comes out to 0.002. We don't care about water. And you can see these are equal to each other. And so we have from these different substances, both of them have been used up to exact amounts. So there's no strong acid, no strong base left over. So this is called the equivalence point for strong acid, strong base, pH equal to 7. And that's neutral. So when we get into a weak acid, strong base, or a strong base, weak acid titration, we'll have a different story when we get to the equivalence point. So this is an equivalence point. Okay, and then for D, we're going to have the same neutralization reaction. H3O plus OH minus makes H2O plus H2O, BCA. And our initial here is 0.002. And this amount is going to come from the concentration, which is 0.0400, times the liters, which is 0.08. And we get 0.0032. Okay, so you can see that there is more hydroxide than there is the acid. So we're going to subtract the smaller of the two. You would call that the limiting reactant. And this comes out to be 0. And then what's left over here is 0.0012, and that's moles. And then in order to find the concentration of the hydroxide, we're going to divide by the total number of liters. So we started with 100 milliliters, and we had added 80 milliliters, which gives us 0.180 liters. So 0.0012 divided by 0.180. And we get 0.0667 molar. And that's hydroxide. So if we negative log that, we're gonna get a POH, right? Because that's, yeah. Your POH is equal to 2.2. So therefore our pH is equal to 11.8. So it popped up pretty fast there. 1.7 to 2 to 7 to 11.8. And remember, we're always looking at what's left over in solution and how that reacts. Okay, that's part 2. Strong acid, strong base titration. Okay, thank you.